Alright, we're going to deal with a branch of physics that's related to calculus called kinematics. It deals with displacement, velocity, and acceleration. The first thing we need to understand is we're going to be dealing with two-dimensional equations, such as, let's see if I can find that here. We're going to deal with equations like this, where we have two variables, time and displacement. That's going to be where the object is in time. And what we need to understand is this is a two-dimensional function, and we're used to seeing that as a parabola that starts below the x-axis and then moves upwards. But what we're actually describing is motion along a line. You can see right here at time 0, we're at -3, so we're 3 away from some central point and moving to the right along the line. So it looks like this, and you can see the object is moving faster and faster and faster over time, but it's moving along a straight line. As soon as we start talking about moving up and then down and then up again, not on a straight line, then we have to start getting into vectors and dealing with a much more complicated branch of physics. But for the sake of learning calculus and understanding how calculus is used, we're going to stick to motion in a straight line. You can see that along the relationship between the position of an object moving along a straight line, which we call displacement, and the velocity, which is speed and direction, so we can go upward or downward, that is away or towards an object, and then we have acceleration, which is um, the rate at which the speed is changing or the velocity is changing. And in terms of calculus, of course, we have the displacement, and then the derivative of that will be called velocity, and the second derivative of displacement is called acceleration. So just to look at it in detail, we have this moving man object, and what I've done is I've set acceleration at 1 meter per second squared, or 1 meter per second per second. What that means is for every second that passes, the velocity will go up by 1 meter per second. And as the velocity is going up by 1 meter per second, that means the position is going to be moving faster and faster and faster. So if we play this, we can see that playing out as the moving man cruises to a crash here at the end. He's died. All right, now if we look at it, we have a constant rate of change and a horizontal acceleration graph, which basically means acceleration will remain constant, but velocity will be increasing. So we could actually see, as it plays on, at 2 seconds, the acceleration is still 1 meter per second, but the velocity is now at 2 meters per second, and that means the position is a little bit further away in the second than it was in the first second. And as you continue to play on, you can see that the velocity increases, which means the dude is covering more distance in less time, and that's why we have a steeper graph. You may also notice this is a parabola whose derivative is a line, whose derivative is a horizontal line. So that's all stuff that we've seen before. Now all we have to do is use all the things we know about calculus and algebra, dare I say it, to learn how to do the analysis of a particular function which describes a motion along a line. Now I remind you that what we're describing is going to be very simplistic, but the idea is we'll be building the basics or the foundations so that later if you study physics you'll have some more advanced, or you'll have a basic underlying understanding. On page 7 of your handout, there's this problem which deals with the position of a particle moving along the x-axis, so that's moving along a straight line, and it says its position on x is dependent on time according to this particular rule. Time is measured in seconds, the position is measured in meters, and time is positive starting at 0 and moving forward. So here are the instructions. We've got to draw sign diagrams for the particle's velocity and acceleration functions, find the position of the particle at times when it reverses directions, and hence draw a motion diagram. And there is such a thing as a motion diagram where we're just drawing it along a horizontal, but we're going to show this on a two-dimensional graph so we don't have to learn something new. And see at what time is the particle's speed decreasing versus when its velocity is decreasing. And finally, we need to find the total distance traveled by the particle within the first 5 seconds of motion. All of these questions, B, C, and D, can be answered by using our derivatives. So we start with the first derivative, which will tell us our velocity. And the velocity is this quadratic function going from the cubic, just using the power rule. And if we want the velocity to equal 0 to find out when the function is changing its position or stopping, we have to solve this quadratic equation. Oh no. I recognize that 3, 18, and 24 are all multiples of 3, so I divide both sides of the equation by 3, which makes a much easier quadratic expression for factoring. And when I factor, I get t minus 2 times t minus 4 will give us t squared minus 6t minus, or plus 8. Then that tells me that when t equals 2, or when t equals 4, the velocity is 0, which means the object has stopped, and then I have to make a sign diagram. In order to do so, I need to find out the velocity when t is less than 2, so I choose 0. The velocity at 0 is positive, which means the function was increasing. Between 2 seconds and 4 seconds, the velocity was negative, which means the velocity was decreasing, or the function, or sorry, the displacement was decreasing or going towards. And at 5 seconds, we find again a positive first derivative, which means the distance again was decreasing. So, or increasing, sorry. This gives us a sign diagram. Basically, we have a positive first derivative from 0 to 2 seconds. We have a negative first derivative from 2 to 4 seconds, and a positive first derivative from 4 seconds and beyond. So what that means basically is the object was moving away or up or whatever, and then it was moving back in the opposite direction over those 2 seconds, and then it was moving back in the original direction for the remainder of its path. We get to the second derivative, that's 6t minus 18. We set that equal to 0, and we get t equals 3. That's going to be our point of inflection. So we're going to compare the sign diagram for the first derivative against the sign diagram for the second derivative, noting that the acceleration is negative from 0 to 3 seconds. Let me move this down a little bit. Acceleration is negative for the first 3 seconds, and acceleration is positive for the remainder of its course. Now, we take these key points, x equals 0, where we start, x equals 2, where we stopped, x equals 3, where we have inflection, x equals 4, we plug them, substitute them all into the original equation, and that gives us these locations of the particle along a horizontal line. I said make a direction diagram. That's basically a graph. So here's what the graph looks like when I plot all those points. And these are the remaining questions that I have to answer. When is the speed decreasing? Now this is a tricky question because it's also asking when is the velocity decreasing. And a lot of people see velocity and speed as the same thing, but speed is irrespective of the direction, or velocity is just talking strictly about the direction itself. So let me show you what the solutions are to answer this question. First of all, what I want to point out is the object is moving away, and then it's moving, it changed directions, and then it went back the other direction again after 4 seconds. We talk about when is speed decreasing. What we could argue is that the object was slowing down, slowing down, slowing down, slowing down, slowing down, stopped at 2 seconds. And then right here, we could also argue that the object is moving in the opposite direction, but here it's moving faster, and here it's moving slower. So the speed was decreasing up till here, and then we sped up to move away, and then we slowed down to change directions again. So the speed is actually decreasing from 0, oh, that's a typo, that should say 0, from 0 to 2 seconds. So from 0 to 2 seconds, or from 3 to 4 seconds. So again, if you just look at the graph, what we can see is that the object was slowing down as it moved away from the origin. And here, the object was slowing down as it moved towards the origin. So when we're talking about speed, I don't care whether we're talking about going away or towards. The idea is it going faster and slower, or slower than faster? The other question is when is velocity decreasing, and that question can be answered this way. From 0 to 3 seconds, the velocity was decreasing, and so there we're looking at strictly negative acceleration versus positive acceleration. So to answer the velocity question, all we have to do is use our acceleration or our second derivative, and we can answer that question. Or we could look at the graph and say slowing down, slowing down, slowing down, slowing down. And we can actually basically say getting more and more and more and more negative acceleration. And then here acceleration is 0, and now it's just positive forever and ever and ever again. So that's when our velocity is going to increase forever. So it's kind of confusing. What you need to do is probably pause this and think about it and look at the graph and look at these answers to get the difference and understand what's the difference between speed and velocity. The last question was asking what's the total distance traveled over the first 5 seconds. Some people might be confused and find that x of 5 seconds is 20, and say the object moved 20 meters. But what's really going on is that the object is moving 20 meters up in the first 2 seconds, and then it's moving backwards 4 meters in the next 2 seconds, and then it's moving forwards again another 4 meters in the last 2 seconds, and that is a total of 28 meters in total. 20 up, 4 down, 4 back up again, 28 meters total. So once again, you need to spend some time thinking about this, and I think the difference between speed and velocity is probably going to be the most confusing. But if you take the first derivative and use it to figure out intervals of increase and decrease, take the second derivative and use that to figure out where there's inflection, find the value of the function at those specific points to produce a graph, then you can answer any question related to the function just by analyzing your graph. So that's basically the point. So there's really nothing new here. What we're going to do is change a little bit of the language, talk more specifically about speed and velocity, but we're still using calculus. We're still interested in when our derivatives equal 0, etc. So hope that was helpful.